Hello, and welcome to the AES Advanced Enviroseptic Design and Installation course. We hope that at the completion of this course you'll be more familiar with the principles of on-site wastewater processing, and then convinced of the advantage of AES systems to the development of cost-effective and, as we shall see, demonstrably sustainable on-site or decentralised wastewater processing technology throughout New Zealand. The AES system is a passive wastewater treatment system that treats primary treated effluent from a standard septic tank to advanced secondary standard. The purpose of this online tutorial is to provide you with the revision of the principles of decentralised or on-site wastewater treatment and the various methods of achieving the desired outcome currently in use. We will then go on to discuss the AES system in more detail. A lot of information on this course is drawn from the following references and is also available on the Environment Technology website, et.nz. Throughout the course, Advanced Enviroseptic is referred to as AES and Environment Technology as ET. Wastewater treatment can be described as the removal of contaminants from effluent using physical, chemical and biological processes, having the objective of producing an environmentally safe fluid waste stream, making polluted effluent flow safe for reuse. Useful data is obtained from an installed water meter on the outlet from the treatment system, confirming or otherwise that the system is working within its design parameters. An approximation of the water use can also be obtained from a water meter on the water supply to the property if any irrigation use is excluded. BOD, TSS, fecal coliforms are the terms used to describe wastewater test results. BOD, biological oxygen demand, is used as an indicator of organic pollution in water. It is measured over a period of 5 days and is usually expressed as milligrams per litre. TSS, total suspended solids, another measure of effluent quality also expressed as milligrams per litre. This measures the quantity of filterable solids in water. Fecal coliforms. These are coliform bacterium derived from fecal material. They are usually anaerobic, rod-shaped, and are used as an indicator of fecal contamination of water. The number of colony-forming fecal coliforms will also include E. coli, accounted under a microscope, and the units are expressed as a number per volume of colony-forming units, CFU per 100 ml. Nutrient reduction refers to the reduction of phosphates and nitrates and has specific maximum values for sensitive receiving areas, such as the central North Island lakes. Phosphorus removal or reduction is usually not required for discharge to land in New Zealand, as the phosphorus binds to aluminium and iron in the soil. This table provides an overview of the different types of effluent, and you can see how the numbers decrease as the treatment quality increases. You can note test results for the AES system provide results of BOD of less than 2 milligrams a litre and TSS of 3 milligrams a litre. This qualifies as 10 times better than secondary treatment, as defined in Australian New Zealand Standards 1547/2012. On our website there's an 8-minute video that gives you a good visual explanation through the whole testing procedure and the outcomes achieved by AES compared to a conventional pipe and gravel system. Wastewater treatment is broadly divided into 3 categories. Primary treatment is the settlement of solids in a mostly anaerobic environment, usually in a standard septic tank. Secondary treatment is further processing in an aerobic environment. Tertiary treatment is further treatment involving disinfection, often by way of a UV filter or adding chlorine. The minimum size of a septic tank is generally calculated at 3 times the daily wastewater flow, as this will ensure a 24-hour settlement period, even when the tank is 2/3 full of sludge and scum. In general, the larger the septic tank, the better, as increasing the retention time results in better treatment due to the greater interface area between the layers in the tank. A large tank will also decrease the frequency of tank desludging. While necessary, desludging the tank can disrupt the performance of the anaerobic treatment processes in the tank and should only be carried out when the bottom sludge and top crust level has built up to more than half the tank capacity. This can take about 3 to 7 years depending on your wastewater flow. The picture shows a simple way of measuring the amount of sludge. The stick can also be inserted through an inspection port above the inlet. Secondary treatment involves an aerobic bacterial and microorganism process, which result in further removal of dissolved and suspended organic matter from the effluent stream. This usually occurs after primary treatment in a septic tank and reduces BOD to 20 milligrams a litre and TSS to 30 milligrams a litre. Secondary treatment can often be a council requirement due to small area of land available for the disposal field, proximity to surface water, and concern about groundwater contamination. An aerobic environment can be achieved in several ways. 3 methods are described on this slide. Advanced secondary can be defined as BOD of 10 milligrams a litre and TSS of 10 milligrams a litre, or in some jurisdictions 15 milligrams a litre for both. While the first method above can, in some systems, achieve advanced secondary treatment, the other methods listed generally produce a higher quality of treatment. AES uses the third method above and has consistent high-quality test results and can be referred to as an advanced secondary treatment system. In New Zealand, we often use the term package plant as a general term for proprietary secondary wastewater treatment systems. This group of treatment systems can be divided into smaller groups based on the method of aeration. Sand filters and oxygenation ponds have been in use for decades, and many of the more recent systems often incorporate some aspect of these older methods. Tertiary treatment refers to the sterilisation of secondary treated effluent using UV disinfection or some method of adding chlorine to eliminate bacteria and pathogens in general. Increasing the depth of sand beneath the AES pipes is a simple method of reducing the fecal coliform level to close to tertiary without requiring any input. The level of disinfection achieved is determined by measuring the number of fecal coliform forming units, CFUs, in the effluent. Primary treated effluent typically has 100,000 CFUs per 100 millilitres, secondary effluent 10,000 CFUs per 100 millilitres, while tertiary treatment standard requires 100 CFUs per 100 millilitres. An AES system, AES 38R, underwent testing in 2017 and 18 in Rotorua in OSET NTP Trial 13. Recirculating the treated effluent back through the anaerobic and carbon-rich septic tank and adding a Salcor 3G UV disinfection unit to the system. Results obtained in Trial 12 research and development phase showed total nitrogen reduction to an average of less than 8 milligrams a litre, a greater than 85% reduction from influent TN values, and improved BOD and TSS to below test levels. The addition of the Salcor unit in the R&D phase show E. coli and fecal coliforms reduced to 0. This scalable tertiary treatment system's results are obtained with minimal energy and servicing input and one small pump. For more information on Trial 13 and the previous Trial 12, where a single-pass AES system was tested, you can contact ET or visit our website et.nz. Tertiary treatment is required if the effluent is to be reused through toilet flushing, for example, or if the discharge to land is unavoidably close to potable water supplies. Occasionally, the term tertiary treatment refers to nutrient reduction. Most commonly, the nutrients that can adversely affect the environment are nitrogen and phosphorus. Denitrification requires an aerobic process followed by an anaerobic process. Wastewater systems that can achieve less than 15 milligrams of total nitrogen are often required in sensitive lake catchment areas such as Rotorua, Taupo, Queenstown and many others. After primary, secondary or tertiary treatment, the effluent is usually required to be disposed of to ground, where soil bacteria and microbes in general are able to consume whatever nutrients are left after the treatment. The method of this disposal can include trenches or beds in the soil, either gravity-fed or dosed with a pump or siphon. The pump or siphon systems are referred to as low-pressure effluent distribution, LPED systems, unless pressure compensating drippers are used, in which case more pressure is required in the dosing system. Raised beds or mounds with distribution pipework for when the proximity of groundwater is a seasonal or permanent issue. Raised beds are usually fed by a pump. Evapotranspiration beds often incorporate sand to aid transportation of the liquid to plant roots. In these beds, transpiration of liquid by plants to remove water and nutrients is used, as well as absorption of liquid through the base of the bed, particularly where downward percolation is compromised by clay or other restrictions. Subsurface irrigation using pressure-compensated dripper lines, drip irrigation. Spray irrigation to land is usually not acceptable in small-scale on-site wastewater treatment systems. The disposal to ground in this drawing is by way of pressure-compensating drippers. This refers to drippers that require a minimum pressure to operate and which maintain a constant flow rate as pressure is increased. This allows even distribution over even uneven ground. Scour valves are fitted at the end of each dripper line to enable flushing of accumulated solids at regular maintenance intervals. In its simplest form, an AES system disperses the advanced secondary treated effluent passively into the soil below the AES sandbed. As we now know, in order to achieve secondary wastewater treatment, an oxygenated environment is required. Secondary treatment systems are all based on providing this aeration in some way. The AES system pipes achieve this in the simplest possible manner by differential venting, which provides a chimney effect. Air is drawn into the low vent at the inlet at the end of a line of AES pipes and exiting at the end of the AES pipe system to a high vent outlet of at least 2 by 50 mm or 165 mm vent in diameter, positioned at least 3 meters in elevation above the low vent. This high vent is best positioned on an adjacent building or other support structure with its own pipework independent from other pipework carrying untreated effluent. The key to the success of the AES system without any mechanical intervention is the passive airflow through the AES pipes hosting the microorganisms. Careful attention to the airflow path is an essential aspect of an AES design and installation. High and low vents can be at the AES bed or remote from the bed. If a bed is split into 2 or more subsystems, the vents can be connected with a manifold. Any low points in the vent pipework must have holes drilled and the pipe laid in drainage metal and filter cloth to allow any condensation to drain. If supported by a building, the high vent should be positioned in the same way as a terminal vent, above the eaves and with appropriate setbacks to windows and doors. Pipework used to transport effluent to the bed should be excluded as much as possible from the air venting requirements. Capping the septic tank outlet T, as in the drawing below, is one way to do this. If a distribution box is used, an 88-degree bend on the inlet, as in the photo, also achieves this and provides a suitable water trap to isolate the airflow. AES systems work best when one row is filled to overflowing rather than 2 to 3 rows partially filled. Thus, when rows are connected in series, the first row is likely to receive more effluent than the last row. While this initially appears counterintuitive to a standard primary treated effluent dispersal to soil, we need to consider the benefits of the rising and falling of liquid in each row of AES pipe. This is referred to as the lung effect and provides optimal conditions for aerobic microbes as the liquid level rises and falls within the pipe system. When the aerobic bacteria have colonized the pipes and a stable community established at around 21 days, a biomat is created, which allows the effluent to extend the entire length of the pipe. treated effluent, stripped of the majority of its food values by these organisms, then slowly seeps out into the system sand. The grain size of this sand allows effluent to travel slowly throughout the sand bed, where further habitat for microbes is provided. In this way, the base of the AES bed receives an even amount of effluent, stripped of BND, BOD and TSS to less than 3 milligrams per 100 millilitres, or 10 times less than secondary standards by test results. Note, the last row will only receive effluent when there is peak occupancy in the home. These pictures show the interior of actual AES pipes after 10 years of use in a restaurant wastewater system. As the scum tries to exit the pipe through the skimmer tab holes, the tabs hold the scum and retain it within the AES pipe environment, which allows the bacteria to process and consume those solids. Another crucial component of the AES system is AES system sand. This is coarse washed sand with less than 2% silt passing through a number 200 sieve, 75 microns. Washed concrete sand generally meets the required specifications, as do the samples pictured. If you can't get a specification grading sheet from suppliers of sand and aggregate, sand can be tested free of charge by sending 2 cups of sand to ET, or if you intend to be using a variety of different source sands, by purchasing a sand spec checker. In this slide, the spec checker components are shown on the right. Sand is put in the middle, the coarsest screen, and washed. For AES system sand, we are interested in 2 things: the amount of coarse sand that remains inside the inner screen, and the amount of fines that are washed through the finer screen. If a sand analysis graph fits inside the sand envelope pictured on the left-hand side, it can be used as AES system sand. Here is a cross-section through a 2-row system and surrounding system sand. The actual infiltration footprint of AES pipe system equals the required length multiplied by 1.35 metres in this 2-row setup. This is the total width of the sand bed surrounding 2 rows of pipes. The following slides deal more specifically with the AES system. AES is a secondary wastewater treatment system consisting of a septic tank, followed by AES pipes laid level in a sand bed. The AES pipes receive primary treated effluent from the septic tank. Passive aeration of the pipes creates an aerobic environment both within the pipes and the surrounding sand bed. AES was invented by David Presby, president of Presby Environmental of New Hampshire, USA. Presby's experience as a drain layer, designing, installing and troubleshooting all types of septic systems, led him to invent something better, which would also protect the groundwater resources. On this slide, the items to note. AES system has been in use for more than 30 years. There are now around 500,000 systems installed in the US, with over 80,000 in the state of New Hampshire alone. 90% of all standalone wastewater processing systems installed in New Hampshire are AES. Some US states now permit discharge after treatment by AES directly into waterways and for reuse without disinfection. AES has been independently tested by international organisations recognised by JASANS, the Joint Accreditation System of Australia and New Zealand, NSF International in the US, the Public Health and Safety Organisation, BNQ, the Bureau de Normalisation in Canada, SAI Global in Australia, and OSET NTP, the On-Site Effluent Treatment National Testing Programme in Rotorua, New Zealand. AES has been tested 4 times by international accredited agencies since 2005. Tests were conducted over a period of 42 weeks compared to Australian requirements of 26 weeks. ET installed a standard AES system at the Rotorua OSET NTP facility in Trial 12, which ran from October 2016 to July 2017. The system was installed above ground and in a lined bed to allow it to take part in this trial. Additional P-metal was installed beneath the bed to prevent additional treatment occurring as the effluent travelled sideways to the underdrain, collecting the treated effluent. In this way, the system tested mimicked a bottomless AES system as much as it could. The largest AES system designed and installed to date is at Blodgett Landing in the town of Newbury on the edge of Lake Sunapee, the largest freshwater lake in New Hampshire, USA. The peak load is 198,000 litres per day, with average flows of 85,000 litres a day. That can be compared with the flow from a 3-bedroom house, which is around 1,000 litres a day. So this system is designed to cope with a flow of in excess of 200 3-bedroom houses. The system bed area is 1,900 square metres. While having to comply with the Environmental Protection Agency groundwater discharge standards, the system also had to handle substantial seasonal load variations from tourism. Existing sand filtration beds were upgraded to AES in 2011. In August 2013, when the AES plant had its operating licence renewed, the required testing interval was increased, as the testing regime for the previous 2 years had produced consistently high-quality results. A summation of the essential aspects of an AES system. The passive treatment of primary effluent to advanced secondary standard at a rate of 38 litres per day per lineal metre of AES pipe. Each length of AES pipe will treat 114 litres a day to advanced secondary standards. AES pipes retain all suspended solids within the pipe system, with graded sand performing the final polishing of the effluent to the standards certified by NSF, BNQ, OSET, and accepted by SAI Global as complying to the performance criteria requirements of Australian New Zealand standards and as an alternative solution for the New Zealand Building Code. AES can be retrofitted to all existing septic systems and can be used for black and grey water or just black water. In 2012, the AES system was introduced to New Zealand by Environment Technology Limited after international research to find a wastewater treatment system which would avoid the high capital and inevitable maintenance costs of other available packaged plants. AES is approved for installation in all New Zealand council areas. Local and regional councils have design requirements specific to their areas and rarely rely solely on Australian New Zealand standards, nor TP58 or that document's replacement, GD06 in the Auckland region. Wastewater system designers are familiar with the relevant regulatory authority-specific local requirements. As all designs are peer-reviewed by ET, councils are familiar with the requirements for ET's signature on submitted designs for building consent processing. A single compartment septic tank is required and should be installed with sealed connections to prevent ingress of water from the surrounding soil. The AES system works after all types and brands of septic tanks that meet the sizing requirements required by AES New Zealand standards, TP58, GD06 or other council regulations. If the path of airflow between the low vent and the high vent passes through the septic tank, then the septic tank lids must be airtight, and an AES bed retrofitted behind an existing septic tank must have the tank vent replaced with a cap, if that is the only practical method for providing for air passage. Pictured to the left is a 4,500 litre round septic tank and a 3,300 litre rectangular septic tank. To the right is a 3,300 litre septic tank with a built-in pump chamber. ET does not recommend and would only approve in exceptional circumstances airflow across the top of the septic tank. Designers are required to provide an alternate air path around the septic tank if the terminal vent at the building must be used as the high-level air outlet vent. This is to avoid the risk of a blocked filter also blocking the airflow through the tank. Tank lids are required to be sealed in this case to isolate any air from the septic tank. If you are required to fit a filter, examine these two drawings. A is a septic tank at normal operating level and without an outlet filter. B shows a septic tank with elevated operating level due to blocked or partially blocked outlet filter. Even if the elevated operating level in the tank is temporary, a proportion of the scum or crust can remain blocking the airflow through either the inlet or outlet when the tank level drops. While there is no requirement for a septic tank to be fitted with an outlet filter, when used in conjunction with an AES system, some councils require an outlet filter to be fitted. If a septic tank filter is fitted, owners must know how to access and clean it. Instructions for this procedure must be made available to both initial and all subsequent system owners. Instructions for cleaning, or at least notification that a filter is fitted, must be attached nearby to the filter housing in a permanent and obvious position. Something similar to, if this tank filter requires cleaning, remove this septic tank outlet inspection cover and wash the filter over this opening so that the filtered material is washed back into the tank. Designers are required to provide an alternative air path around the septic tank if the terminal vent at the building must be used as the high-level air outlet vent. This is to avoid the risk of a blocked filter also blocking the airflow through the tank. Tank lids are required to be sealed in this case to provide a sealed air passage for venting purposes. As you now know, an AES system consists of a primary septic tank and ribbed 3-metre-long AES pipes, 300 millimetres in diameter, installed in a sandbed. This picture shows a cross-section of an AES pipe, and you can see that they are made up of a bioaccelerator pad attached at the pipe base, and this is surrounded by a thick layer of coarse, randomly oriented plastic fibres. This layer and the others serve as an attached culture system, providing an extensive surface area on which microbial biofilms can grow. A geotextile fabric surrounds the plastic fibre layer, further supporting the growth of these microbial biofilms. Pipes must be installed with the bioaccelerator pad at the base of the pipes. In this cross-section of an AES system pipe in use, we see that the scum is floating to the top and sludge sinking to the bottom of the pipe. The liquid level rises and falls within the pipe with hourly or daily variations in flow, and as the liquid component flows through the pipe perforations, while the scum and sludge are retained within. Plastic skimmers extend inwards from each hole. These skimmers help capture grease and suspended solids, preventing them from escaping through the pipe perforations. Aerobic bacteria therefore have the opportunity to thrive with the alternation of liquid effluent level. There is a cross-section of the various layers making up the pipe in place. The bioaccelerator pad is coloured blue in this representation. The other key component of the AES system is that the pipes are installed in clean coarse sand. This second process mirrors that of a sand filter, which has been in use in water and wastewater processing for a very long time. These pictures show the lightweight and flexibility of AES pipes. They can bend to 90 degrees in one 3-metre length. AES pipe has been tested to treat 38 litres of primary treated septic wastewater per lineal metre of AES pipe per day to a standard which is 10 times better than that required for a secondary standard treatment, according to Australian New Zealand Standards 1547. The number of AES pipes required for any specific design depends upon the calculated average daily wastewater flow. To facilitate the hosting of microorganisms or aerobic bacteria, every lineal metre of system pipe provides 7 square metres of biological surface area to assist the treatment bacterial process. AES pipe provides protection of the receiving soil, preventing the build-up of biomat at the receiving soil interface that causes progressive failure in other septic treatment systems. Individual pipes are interconnected with a plastic clip AES coupling, which is a band which clamps to the circumference ridges on each pipe, with the fabric layers temporarily folded back. The coupling features a snap-together locking device and ridges that are designed to fit over the ridges of the AES pipe to create a quick and easy way to securely join the pipe sections together. The maximum length of a row of AES pipes is 30 metres, that is 10 3-metre lengths of AES pipe joined together with couplings to make one long row. An offset adapter is a 300mm diameter plastic end cap with an offset hole designed to accept 100mm drain waste vent DWV pipe. This pipe may be part of the raised connection or an air inlet vent and should not be inserted further than 100mm through the hole. The hole in the AES offset adapter is always installed at the top of the AES pipe or at the 12 o'clock position. The photo shows a raised connector, so called because it needs to be raised up until the top edge of the pipe is level with the top of the AES pipes as shown. Larger AES systems are those defined as being over 2,250 litres a day, which equates to 20 lengths of AES pipe. With these, a distribution box is needed to split the waste stream equally into as many subsystems as required. For example, if 4,560 litres per day is the design influent, then we would divide that figure by 38, the standard rate of influent per metre of AES pipe, which equates to 120 metres of pipe. Divide this by 3 for the metre lengths, and we come up with 40 pipes, which is 2 subsystems of 20 pipes each. These calculations can be simply made using the AES calculator, which we will discuss in the next video. For distribution box configurations, all AES rows must be equal length. All AES rows must be level. The distribution box must be level and on solid foundations. Flow equalizers are required on all outlets and can be turned by hand easily to equalize the outflow to each row. Distribution boxes with 4 holes, 7 holes and 9 holes are available from ET, along with risers to bring the box up slightly above ground surface level. Inspection ports are an optional addition to bed extensions to monitor the performance in the bed itself. We will break this presentation here at approximately halfway and continue with the remainder of the presentation in a separate video.